This is an equilibrium problem involving gases, where we have the equilibrium equation given, and our equilibrium constant is given as K sub C. And since our quantities are in partial pressures, we need to do the conversion of K sub C to K sub P. They're related by this equation. Delta N gas is the moles of gas in the products, and then we subtract the moles of gas in the reactants. Product has 1 mole of gas, our reactants have 2 moles. So delta N gas is 1 minus 2, so it's a minus 1. So we have K sub P is going to equal Kc times RT to the minus 1, which is going to be equal to K sub C divided by RT. So we have 5 divided by 0.08206, and our temperature is 600 K, and we find K sub P is going to be equal to 0.1016. Alright, so if we go back to our ice table, we have our balanced chemical equation. We start with 0.21 atmospheres of each of these gases. We don't have any product. It's a 1:1:1 mole ratio. The equilibrium amounts are the initial plus the change. So now we can substitute into our equilibrium equation. So K sub P is going to be the pressure of the phosgene divided by the pressure of carbon monoxide and Cl2. We can sub in our values. .21 minus x times 0.21 minus x. Okay, our equilibrium concentration equilibrium constant is fairly high, so I don't think we can do the approximation, but let's check. Is the approximation okay? Well, 1000 times K is going to be equal to 101.6, and that is much bigger than our initial concentrations. So the approximation that would simplify this math is not okay. So we have to solve this. Probably the easiest way is to solve it via the quadratic equation. So we have 0.1016 is equal to x. We do FOIL here, and it would be multiply the first, the outer, the inner, and the last. So we have 0.0441 minus 0.42 times x plus x squared. Okay, so for x, we'll cross multiply here. So we have 0.1016 and we're going to multiply all of these things by that constant factor. Alright, so we do that. We have 0.00448 minus 0.0427 times x plus 0.1016 times x squared is equal to x. to solve for the quadratic, we need to get it in the form of ax squared plus bx plus c is equal to 0. So we're going to subtract x from each side of the equation. So we have this minus x, so that's going to be minus 1.0427 times x. So rearranging. Oops. Alright, so this is A, this much is B, this much is C. If we solved via the quadratic equation, we would get two roots, and the two roots that we would obtain in this case, we have x1 is 10.26, and the second value of x is 0.0043. Now, when we solve via the quadratic, there's always one root that makes no physical sense. There's no way we can lose 10 atmospheres, and we only have 0.21 atmospheres to start. So we know that this is nonsense. This doesn't make any sense as a possible root. So we know this has to be the correct answer. Now that we have x, we can go back and answer the question. So the question here is, we want the equilibrium partial pressure of the three gases. So the partial pressure of carbon monoxide at equilibrium is the same as that of Cl2, and that's 0.21 minus x. So within sig figs, our answer is 0.206 atmospheres. And for the phosgene gas, at equilibrium, our phosgene gas is equal to x. So that's 0.0043 atmospheres. Okay, so we had to do a lot of work for this problem, but the general process is the same. We have an ice table, an equilibrium concentration, or equilibrium expression. We solve somehow for x. Once we have x, we go back and answer the initial question.